morning, class.
Morning.
How are you guys doing?
That's math.
Yeah, I know. It's just another bright day in geometry. Today, we're going to recap a little bit on stuff that we've been learning. So, yesterday, you noticed that I put up the formulas that we did to do volume of a cylinder and also surface area of a cylinder. Okay, so before we go on to learn more complex shapes and their volumes and areas and stuff, we are going to just focus in more on this and how this can actually apply to real life. Isn't that great? Math does that to you. All right, so we're going to start off. I'm handing you each a sheet of paper. What I want you to do is divide it, fold it in half, and you're going to actually kind of, I would have scissors, but I kind of forgot them today. So you're just going to fold it equally in half to divide it into 2 equal rectangles. Okay? And just try to divide it as carefully as you can, and you're actually going to separate it. So you're going to kind of rip it apart. Okay? And this will all make sense in a second, I promise. All right, we'll see how this is a test to see how your tearing skills are. All right, yeah, good. Okay, so once you tear them totally apart, notice that you'll have, what kind of shapes are these?
Rectangle.
Yes, very good. Okay, so they are pretty much equal in size and in shape. Agreed? Okay, now, normally, you know that this is a poor school, so we don't have the supplies you need. But normally, if we had tape, you would tape one cylinder so it's short and squatty, okay? And I want you to show me what the other one would look like if you folded it so it was long.
Like hot dog style.
Yes. Okay, good. So you end up getting something that looks like this, okay? Now, which do you think they both have the same volume? They both have the same area. Clearly, if this is a rectangle, length times width, okay, they're the equal rectangles. They have the same surface area. But what about volume? What do you guys think? Do you think they have the same or different?
Well,
I mean, they're the same piece of paper. You just folded it differently. Do you think it's going to be the same or different?
I think it'll be the same.
Okay, what do you think? You think it's going to be the same? All right, so before we answer this question, okay, I want you to think about how this can apply in real life. Have you gone to the grocery store, wanted to buy some tuna fish? Okay, different brands of tuna fish, right? Some of the cans happen to be just a little bit different of the volume, things like that. So we're going to discuss that more. But before we go into that, I'm going to show you a very short video clip about how this can apply in a cheese factory. Okay? And so we're going to learn about this, and hopefully the sound will cooperate. Okay, let's see. Technical difficulties.
Yeah, look at a little volume guy down here.
Oh, good. Oh, you guys have been learning a lot in your computer class. Okay, I'm so impressed. Oh, okay, hold on. Let me just turn it up just a little bit more so you guys can actually hear. Okay. Get started. Oh, okay.
Packaging can be a significant part of a manufacturer's costs in preparing a product for sale. Let's suppose that a cheesemaker has been selling his product in square and rectangular packages wrapped in plastic, and that the amount of plastic used is directly related to the surface area covered. The greater the surface area, the more packaging required, the higher the costs. The cheesemaker has been producing cheese blocks, square prisms with dimensions of 3 by 3 by 2 inches. He learns that many high-end stores display and sell cheese as rounds rather than blocks. He is considering shifting some of his production to making rounds that contain the same amount of cheese as the squares. But he has to consider the implications, such as cost. How much will it cost to package the rounds of cheese compared to the square blocks? Let's suppose the manufacturer has a constraint due to store preferences. For display, the stores prefer cheese products to be no more than 2 inches high, the height of the cheese blocks he now makes. The cheesemaker wants to determine if it makes financial sense for him to produce rounds the same height that contain the same amount of cheese, the same volume. The volume of the cheese squares in cubic inches is 3 times 3 times 2, which equals 18. Using the formula for the volume of a cylinder,
And this is what you guys learned yesterday.
cheese rounds with the same volume and the same height would have a radius of 1.69 inches. Now the cheesemaker wants to figure out the amount of packaging material needed for cheese rounds versus cheese blocks. To do so, he must calculate the surface areas of both. Remember, the surface area of a solid with flat faces is the sum of the areas of all of its faces. The cheese block he's been selling has dimensions of 3 by 3 by 2 inches. He substitutes those numbers into the formula for the surface area of a square prism. A block of his cheese has a surface area of 42 square inches, so it needs about that much packaging, just a little more since the edges will overlap. Now, what about the rounds? The surface area of a cylinder is the area of the 2 end circles plus the area of the curved part. The area of the curved part is the height of the cylinder times the circumference of the circle, since that part unwraps to form a rectangle. The manufacturer substitutes the numbers for the cheese round's height and radius into the formula and determines it has a surface area of 39.2 square inches. That's 2.8 square inches less than the surface area of the cheese block. So each round would require 2.8 square inches less plastic wrap than a cheese block of identical volume. Put another way, it would take about 7% more wrapping to cover a square block than to cover a round. So with the same amount of plastic that could wrap about 100 square cheese blocks, the cheesemaker could wrap about 107 rounds. By calculating surface areas, this savvy manufacturer has determined he could package his product more efficiently, which would save him money. Now that's good business.
All right, class. So, I know that it was kind of, some of that was hopefully made a little bit more sense, especially after seeing a real-life application. So that is actually what they actually do in, in cheese factories. So it's very good to have that going on. So I'll leave that. I forgot how to get it into the slide. Oh, yeah, no. I have it. Okay, so basically what you should have taken away from that is that surface area is going to end up being a little bit different, okay? I'm sorry, the volume is going to be different. Surface area, okay, you took a rectangle and we measured it earlier yesterday and we found out that they have the same surface area. But when we folded it like this, what's changed on top? What do you notice about the circles? One's
Bigger.
yeah, one's bigger, which means that the radius of one is bigger than the other. Very nice. Yes, I'm loving your enthusiasm here. So that is changing the surface area. Now, if we were able to be a richer school, we'd have some more money so we could have these supplies. But what I want your homework tonight is going to be to go home. You're going to take your cylinders that you're going to tape up at home, and you're going to use rice. And what you're going to do is you're going to put the cylinders inside like this. You're going to fill the tall one all the way to the top with rice. And then you'll notice that as you take it out, it won't fill up the entire bigger one. This volume is bigger because of the bigger radius. Even though it's the exact same surface area, different volume. Okay? So the homework for tonight, you're going to be going grocery shopping. Yay! All right? So you're going to be going and finding the volume and surface areas of different items in your grocery store. That means that you're going to have to make sure that you study the homework you had due today, which was computing the surface area and volumes. Okay? So at the grocery store, you're going to have to take a little measuring tape, and yes, you're going to look silly, and people are going to stare at you like, why on earth are they measuring food? But you're going to actually measure them, or if you feel insecure, you can always buy it and measure it at home. But you can measure them in the grocery store, write your dimensions down, go home and calculate it, and you're going to bring it in tomorrow. Okay? And then I also want you to identify a grocery product that could be made with less lateral surface area. Okay? So that's your assignment for tonight, and good luck. I'll let you guys go ahead and hop to it.